we start with the proceedings of the day, we will just recall the things which we have discussed in the previous class. So, as you all aware that we have been discussing about the radioisotopes, wherein we have started the discussion from the very basics of atoms, wherein atoms contains protons, neutrons, and electrons. As I told you, the nucleus of an atom is going to contain the protons and neutrons, wherein the electrons are going to present outside the nucleus. The protons are positively charged, wherein the neutrons doesn't have any charge. The electrons are negatively charged, and these are the very basic things of atoms, wherein we also discussed about the mass number that includes the number of protons and number of neutrons, and the number of protons is also called as the atomic number. We then moved on with the discussion of radioisotopes, wherein we actually discussed what is the definition of isotopes, wherein the atoms of the same element having same atomic number but different number of neutrons. So that is called as isotopes. Okay, and we discussed some examples of isotopes, and then we moved on with the radioisotopes, wherein you have the unstable combination of protons and neutrons. So that results in the formation of radioactivity, and the process in which the production or the release of the protons and the neutrons, we call it as radioactive decay. I told you the analogy of carrying a book for better understanding. I hope you are able to remember that. And then we started with the discussion of alpha radioactive decay in the previous class. So now we will be moving on to the beta radioactive decay. As I told you, in the alpha radioactive decay, it involves the production of two protons and two neutrons, wherein the mass number becomes 4 and the atomic number becomes 2. All right. Now we are going to start with the next type of decay. Next type of decay, and that will be beta radioactive decay. So that is going to be the beta radioactive decay. So beta radioactive decay basically involves the emission of beta particles. Beta radioactive decay produces emission of beta particles, and this beta particle contains contains a fast moving electron emitted from the nucleus. Okay, so beta radioactive decay involves the emission or release of beta particle, and a beta particle is going to contain a fast moving electron emitted from the nucleus. Now you should think logically, as I told you in the beginning of the class itself, that some people are now joining. Okay, so if you take the atoms in the nucleus, we are going to have protons and neutrons, and electrons are present outside the nucleus. But this is controversial with this definition, where we have a fast moving electron emitted from the nucleus. How is that possible? Any guesses, people? I expect responses from the students. I told you in the nucleus of an atom, as we discussed in the previous class, it is going to contain protons and neutrons. Electrons are only present outside the nucleus, correct? I think we actually already discussed the basics of atom. Now, a beta particle is defined as a fast-moving electron emitted from the nucleus. How? Any answer? No responses from the students. Why? Students, are you listening?
Yes, sir. So from the nucleus,
Yes, sir.
like,
Everybody is listening, right?
yes, sir.
Yes, sir.
Okay.
Yes, sir.
So,
Yes, sir.
the question which I asked you is, the nucleus is going to contain only protons and neutrons, and the electrons are present outside the nucleus. But that is actually a unique or an universal statement, with an atom. But here the point is, a beta particle consists of a fast-moving electron emitted from the nucleus. So when you think logically with this particular diagram, it is controversial. But then we have to understand a very important thing. So it is very true that the nucleus is going to contain only protons and neutrons. There is no doubt in that. Okay? But what happens in the case of beta radioactive decay? What happens in the case of beta radioactive decay is a neutron present in the nucleus, releases an electron and a proton. So this is the basic idea that what happens in the case of beta radioactive decay. Okay, so beta particle is going to be a fast moving electron emitted from the nucleus. Now, as we all aware that electrons are actually present outside the nucleus, but here in the statement we can understand that it is going to release a fast moving electron emitted from the nucleus. Sorry. So it is going to contain a fast moving electrons emitted from the nucleus. So how is this electrons produced? The question. The answer is very simple. Inside the nucleus we have neutron. A neutron is converted to, or we can say that a neutron releases an electron and proton. Okay? So what happens now, you have to understand another important concept here, only then you will be able to understand. Another important thing is the mass number of the element doesn't change. But the atomic or the proton number increases by 1. You have to understand this. Now the point is, Tanushri raised hand. Yes, Tanushri.
Yes, sir. I have a question.
Yes.
If the neutron can release an electron and a proton, will it need sufficient amount of energy from external source?
No, Tanushri, you have misunderstood that. You are not supposed to think about energy here. The point is, we are speaking about decay. Now, the basic idea here is, inside the nucleus, you have an unstable combination. And because of that unstable combination, we have beta radioactive decay. And for this conversion, it doesn't require energy. In order to attain a more stable state, it is getting converted into electron and the proton. So that is the point you have to understand. Got it?
Okay, sir. Yes, sir. Yes, sir.
Okay. So once again, I am telling you, in the case of beta radioactive decay, it is going to be a fast-moving electron emitted from the nucleus. But then in the nucleus, we don't have electrons. The answer is very simple. The neutron which is present in the nucleus is released as electron and proton. Now the point which you have to understand is, as we all know, mass number is the total number of protons or the atomic number plus neutrons. It doesn't change. Why? Because the neutron is lost. It is -1. The neutron is lost. It is -1. But it again gains a proton. So it is +1. So cancel. So there is no change. You have to understand this. The atomic number or proton number increases by 1 because to the element the proton is added. The proton is added. So that is the reason wherein you have no change in the mass number and you have a change by 1, increase by 1 with the atomic or proton number. Okay, so I repeat once again, the mass number of the element doesn't change because a neutron is lost. A neutron is lost, it is -1, but at the same time, since it is added with the proton, there is no change. But the atomic or proton number increases by 1 because there is an increase in the proton number to 1. So this is the basic calculation for doing the beta radioactive decay. So we will just see with the specific example of this beta radioactive decay, you will be having a better understanding of this particular process. 1 minute. Okay, sorry for the gap. Now, we will go with the specific example. Yes. Speaking about this specific example of this particular beta radioactive decay, so now the specific example of this, let me tell you, we'll take polonium. This is polonium, which has the mass number of 218 and atomic number or proton number is 84. So now this is going to undergo beta radioactive decay. So let us see what happens. So this is going to produce a beta particle whose mass number will be 0. It is going to contain an electron. Correct? If you take the definition of beta radioactive decay, it is a fast moving electron. It is going to contain only one electron. So it is represented by the beta symbol. The mass number is 0. Why? We don't have any protons and neutrons there. So we have only electrons. So it is represented with 0 and 1 electron. Got it? Now, this PO, that is polonium, is converted to astatine. It is converted to astatine. Okay? And here, if you see the mass number, it is 218 again here. Correct? And if you take the atomic number, it is going to be 85. It is going to be 85. Now, I hope you can understand. Polonium has the mass number of 218, and here again it is becoming 218. Why? Because a neutron is lost by polonium, and a proton is gained by astatine. That is the basic idea. A neutron is lost by polonium, and a proton is gained by astatine. So there is no change in the mass number. But if you take the proton number, since there is a gain of the protons, now this 84 becomes 85. Okay, so now this is a very good example of a beta radioactive decay. I'll just write one more example of a beta radioactive decay, and after that we'll move on to the next one. So we have thorium. Okay, so we have thorium. Which has the mass number of 234 and atomic number of 90. Okay. Now this again undergoes beta radioactive decay, wherein it is converted to palladium. It is converted to palladium. And here again the mass number is not going to change, but then the atomic number increases by 1. That is 91 plus beta radioactive decay, that is beta particle. We have beta particle with mass number 0 and 1 electron. So we have this thorium which is converted to palladium with the increase in the proton number and no change in the mass number, and you have the production of beta radioactive particle. Okay. People are able to follow this.